Hello there everyone, hope you all are doing fine at your places. Today we'll be finishing our chapter of 11th class that we have started in the previous video, that is mathematical induction, as you all know. And we have successfully done 3 examples in the previous video, and today we will be starting our work with the example number 4. Now, from example number 4, most complicated sums that are involved in mathematical induction are started. So I'll be trying to just explain the methods involved in these kind of sums in the easiest manner. Okay, so watch this video till end to just clear your concepts of these kind of sums. So let me write the statement of example 4. In this example, we have to prove that for every positive integer n, 7 raised to power n minus 3 raised to power n is divisible by 4. So we have to prove it using mathematical induction. As you know, we'll go step by step, the steps that we have learned in our previous video. So firstly, we have to check that if this given situation is true for n is equals to 1. Now put n is equals to 1, you will get 7 minus 3, which means 4. Now you know that 4 is divisible by 4, right? So you will write that it is true for n is equals to 1. Now we have checked the given situation, the given case for n is equals to 1. Now what was the second step that we have learned? We have to assume that result is true for n is equals to k. So put n is equals to k. 7 raised to power k minus 3 raised to power k. Now in the previous sums, we always get an equation that left hand side is equals to some right hand side, but here in this case we have no equation, so we will make one from our own. 7 raised to power k minus 3 raised to power k, we have assumed that this is true. This is true means this is divisible by 4. So if it's divisible by 4, then we can write it as a multiple of 4. So we can write 7k minus 3 raised to power k is equals to 4q, which means that this is some multiple of 4, or this is divisible by 4. So this will be our first equation. Now in this, you don't have to add or subtract anything on the left hand side and the right hand side. You have to consider an equation. This is where the difference begins as compared to the previous examples. Now you have to consider an equation. What's that equation? Just substitute k plus 1 in place of n. You get 7 raised to power k plus 1 minus 3 raised to power k plus 1. Alright, now watch this video from here very carefully, because now I'll be telling you step by step that what you have to do and how you are going to solve this. From this equation, you have to reach to the first equation by hook or by crook, by adding or subtracting anything that you would like to add or subtract. You have to reach to this equation so that you can equate it to 4q, and then you can take 4 common from the other terms as well, and then if 4 can be taken out as a common factor from all of the terms, it means the result we get is divisible by 4. That we have to prove. Okay, so we know that here it's 7 raised to power k. So firstly, we will just split the powers. We can write 7k multiplied 7 raised to power 1 minus 3 raised to power k plus 1. Okay, so now here it's 7 raised to power k minus 3 raised to power k. So what we will do, 7 raised to power k minus 3 raised to power k and plus 3 raised to power k, so as not to disturb the concord of the equation. Now it's 7, it will remain outside only. 3 raised to power k plus 1. 7k minus 3k, can you write it as 4q? Yes, 4q plus 3 raised to power k multiplied by 7 minus 3 raised to power k plus 1. From where you have got this? From first equation. Now 4q, now multiply 7 inside. 7 multiply 4q plus 7 multiply 3k minus 3 raised to power k plus 1, correct? Now you can take 4 common from the first term, but you have to make statements such as you can take out 4 common from these terms as well. So we will simplify it a bit. Just this step, most of the students get confused in this step only, otherwise the sum is very easy, you will see yourself. Split the powers again so that you can take 3 raised to power k as a common factor. So 3 raised to power k multiply 3 raised to power 1, right? Now what is the common factor? That is 3 raised to power k. What's left inside 7 minus 3? 7 multiply 4q plus 3 raised to power k multiply by 4. Correct? Because 7 minus 3 is 4. Now 7 multiply 4q plus 4 multiply 3 raised to power k. It means we can take 4 as a common factor. 7q plus 3 raised to power k. Now it is clear that this is divisible by 4 because 4 is its common factor. Now what was it equal to? It was equal to this thing. So yes, we have proved that our given result is true for n is equals to k plus 1. We have proved that if we put n is equals to 1, the term is divisible by 4. We have assumed that it will be divisible by 4 as well when we put n is equals to k. And now we have proved that if we put n is equals to k plus 1, still this term is divisible by 4. This is how you have to proceed in sums like these. And at the end you can write that it's divisible by 4. It means p of k plus 1 is also true. So by principle of mathematical induction, the statement is true for every positive integer n. Alright, this is the sentence that you have to write at the end. I hope this was very helpful for you because most of the students get confused in these kind of steps, that how to simplify, how to reach first equation again. So if you have literally some confusions still, you can DM me on my Instagram ID, which is given in the description, and you can use the comment section as well. So I'll be more than happy to assist you there. So let's move further. This is our fifth example. In this we have to prove that 1 plus x raised to power n must be greater than equal to 1 plus nx. It can be greater than, it can be equal to. So firstly we'll do the same. We'll prove for n is equals to 1. Now put n is equals to 1. What will you get? 1 plus x raised to power 1 only, greater than 1 plus x, greater than equal to. Now if it would have been only greater than sign, then it would have been not a true statement. So now it's equal to as well. So it means it is satisfying one inequality. This means result is true for n is equals to 1. Clear? Now we will again assume for n is equals to k. When you will assume, what will you get? 1 plus x raised to power k greater than equal to 1 plus kx. Correct? And you have to write the condition as well simultaneously, that x is given to be greater than minus 1. Now we have assumed this statement, but we have to prove that 1 plus x raised to power k plus 1 is greater than equal to 1 plus k plus 1 multiply x. Okay, so consider that term. Now consider again the left hand side by substituting n is equals to k plus 1. You can write it as 1 plus x raised to power k multiply 1 plus x. Correct? You can write it. Now use this equation. Now you can see that 1 plus x raised to power k is given to be greater than equal to 1 plus kx. So the whole equation will be converted into a linear inequality that will be greater than equal to 1 plus kx multiply 1 plus x. Okay, the complications were till this point only, and I hope that I have cleared most of them. Now it's just a matter of simplification. 1 plus x raised to power k plus 1 greater than equal to, now multiply 1 plus x plus kx plus kx square. Now it's 1 plus k raised to 1 plus x raised to power k plus 1 greater than equal to 1 plus, you can take x as a common factor, 1 plus k plus kx square. So which will give us 1 plus x raised to power k plus 1 greater than equal to. Now you can see that we had to fetch 1 plus k plus 1 multiply x. So we have get 1 plus k plus 1 multiply x, but kx square is an extra term which is here. Now we will use the given condition. What we will write, you had to write here before this step. You will write that x is given to be greater than minus 1. It means x square is greater than 0. So it means x square can be greater than equal to 0 because x is given to be greater than minus 1, so 0 is also greater than minus 1. So x square can be greater than equal to 0, or kx square is also greater than equal to 0. So now if kx square is greater than equal to 0, kx square is greater than equal to 0, then the whole term will be greater than equal to 0, and you will simply get this remaining term because this is given to be greater than equal to 0. So you will just simply omit this term, and now you have got your answer. 1 plus x raised to power k plus 1, 1 plus k plus 1 multiply x. So you can write that it is true for every positive integer n. Okay, so now this is how you can prove the equations, any kind of equation, using principle of mathematical induction. Let's move ahead. This is our sixth example. 2 multiply 7 raised to power n plus 3 multiply 5 raised to power n minus 5 is divisible by 24. We have to prove this using mathematical induction. Again, let's follow the same steps. That is, for n is equals to 1, what will you get? 2 multiply 7 plus 3 multiply 5 minus 5. 2 7s are 14 plus 15 minus 5, that is equal to 24, which is divisible by 24. So for n is equals to 1, it is true. Clear? Assume the result for n is equals to k. What will you get? 2 multiply 7 raised to power k plus 3 multiply 5 raised to power k minus 5. Now again we need an equation. So this example is very much identical to fourth example, in which we considered it as 7q or 4q, I guess, because it was a divisor of 4. Now here we will consider it as 24q, 24l, m or d, any alphabet, because we have assumed that this thing is true. It means, what means if it is true? It means that this is divisible by 24. So we can write it as 24q. Consider this equation as equation first. Now again you have to consider a term. That term can be fetched through substituting n is equals to k plus 1 in the statement. That is why 2 multiply 7 raised to power k plus 1 plus 3 multiply 5 multiply k plus 1 minus 5. You have to reach first equation again as it was in the fourth example. So when we have to reach the first equation, just see the first term, nothing else. Here it is 2 raised to power 7k, but here it's 7 raised to power k plus 1. So just split the terms. 7 raised to power k multiply 7 raised to power 1. 3 multiply 5 raised to power k plus 1 minus 5. Now here 2 multiply 7k, you have plus 3 multiply 5 raised to power k minus 5. So what will we do? We will add the terms which are required to be added, and we will subtract the same terms. Here what I have done, plus 3 multiply 5 raised to power k minus 5 minus 3 multiply 5 raised to power k plus 5, because I have not disturbed the equation, right? You can see, just look at this equation and just add the same terms and subtract the same terms in order to not disturb the balance of the equation. So now these factors will be there only. Plus 3 multiply 5 raised to power k plus 1 minus 5. Now what we have to take as a common factor? We have to take 24q as a common factor, right? 24 as a common factor. So just keep an eye on that. You can write 2 multiply 7 raised to power k plus 3 multiply 5 raised to power k minus 5 is equals to 24q from equation first. So it will be 24q. Then minus of 3 raised to power 5k, 3 multiply 5 raised to power k plus 5. Then here is 7, then plus 3 multiply 5 raised to power k, and split it as well because you will need minus 5. Now 24q, multiply 7 inside, 24q multiply by 7 minus 21 5 raised to power k, because 7 3s are 21, plus 35, right? And plus of 3 5 raised to power k multiply 5 minus 5. Now you can take 5 raised to power k as a common factor. correct? So when you will take 5 raised to power k as a common factor, what will you get? You will get 5 raised to power k as a common factor. So we can take minus of 5 raised to power k, no worries, and here it will be 21. 3 5s are 15, these are getting multiplied, so minus of 15, correct? 35 minus 5, you will get plus of 30. 7 multiplied 24 cube minus of 5 raised to power k, and this is 6 plus of 30, or you can say 7 multiplied 24 cube minus 6 multiplied 5k plus of 30. Now here you can see that we cannot take 24 as a common factor from these two terms, so we have to simplify it a bit more. Now 7 multiplied 24 cube, what you can take out as a common factor, that is 6 minus 6, 5 raised to power k minus 5, this will be left. Now here you have to think very creatively, because 5 raised to power k minus 5 can be written as 4p or 4l or 4m, any alphabet. Let's use 4p because this is a multiple of 4. How? Just simply put k is equals to 1 2 3, just put these value. When you will put k is equals to 1, it will be 5 minus 5 0, it's a multiple of 4, it's a multiple of every number. Now put k is equals to 2, 5 5s are 25 minus 5, that is 20, again it's divisible by 4. Then put k is equals to 3, you will get 5 5s are 25, 5s are 125, 125 minus 5, that is 120, again it's divisible by 4. And similarly it's divisible, it's every factor is divisible by 4, that is why we can write it as 4p, because this term is divisible by 4. Now 7 multiplied 24q minus 24p. Okay, so now you can take easily 24 out as a common factor, 7q minus p. Alright, so 7q minus p, it means you have taken 24 as a common factor, which means this term is divisible of, is a divisor of, or is divisible by 24. This is how you have to prove. Sometimes these kind of steps can be there in your sum, but no issues if you know these kind of tricks and these kind of simple concepts, that which is divisible by what number and what digit, you can easily do that. Nothing, not a big deal, I guess, right? If you find any problem, just DM me so I can help you personally as well. So let's move to the next example. In this example, you have to prove 1 square plus 2 square plus up to so on n square greater than n cube upon 3. We will again use induction, obviously. So firstly, let's do it for n is equals to 1. What will you get? 1 square greater than 1 cube upon 3. It means 1 greater than 1 upon 3, which is true. It means your result is true for n is equals to 1. Assume it for n is equals to k. 1 square plus 2 square plus up to so on plus k square. Now here's one thing before proceeding that I would like to tell you, that you have to write sentences properly, okay, in order to get full marks, because I am just writing short forms in order to just not waste your time, and because you know that what to write and what to not to write. So I am also saying it simultaneously, okay. Greater than k cube upon 3. We have filled n is equals to k. Now k square greater than k cube upon 3. It's a statement in which terms are being added up. So just remind yourself of the first example, the third example, in which we added the same terms on the left hand side and right hand side in order to get our required result. And what was that term? That term was one term next to the last term. Now we have to prove for n is equals to k plus 1. So what we will do, just write the series till k plus 1, because it's 1 square, 2 square, so these are increasing by 1. So the next term will be k plus 1 whole square greater than k cube upon 3. Now if we have added k plus 1 whole square on left hand side, we'll add the same term on the right hand side. Now left hand side is already proven because we wanted k plus 1 at the place of n, which we have got. Now we'll solve only the right hand side, and we want k plus 1 cube upon 3. So let's solve the right hand side. K cube upon 3, just open the whole square, k square plus 1 plus 2k then greater than k cube upon 3, take LCM, plus of 3k square plus 3 plus 6k, correct? Now we want to form the whole cube of k plus 1. So what will be k plus 1 whole cube look like? It will look like k cube plus 1 cube plus 3k square plus 3k, because the formula is a cube plus b cube plus 3a square b plus 3ab square. Okay, so this is what we have to write. Now we have k cube and we have 3k square as well. What we don't have, that is plus 1 and plus 3k. So what we will do, we will add plus 1, we will add plus 1 plus 3k and subtract minus 1 minus 3k from our side. What will you get? Plus 3k plus 1 minus 3k minus 1, then these three terms, plus 3k square plus 3 plus 6k upon 3, greater than a cube plus b cube plus 3ab square plus 3a square b. So you can write k plus 1 whole cube. Now what terms are left? Minus 3k minus 1 plus 3 and 6k. So 3 minus 1, that is 2. 6k minus 3k, that is plus of 3k upon 3. Now we only wanted k plus 1 whole cube, but here are two extra terms. Now you can write that k plus 1 cube, because it's very clear that k plus 1 cube plus 3k plus 2 is always greater than k plus 1 cube, because there two terms more are being added up and there is only single term. So we can write this equation as simply k plus 1 cube upon 3. This is the result that we wanted to get, that 1 square plus 2 square plus k square plus k plus 1 whole square must be greater than k plus 1 whole cube upon 3. So this is the desired result that we have get. It's very simple, just you have to be use your presence of mind that from where we can fetch the result, fetch the required result. Only then you will be able to do these kind of sums, right? So yeah, that's it, and only one example is left, so quickly do it and let's leave then. Here is our very last example of the chapter mathematical induction. Now we all have seen this result, that ab whole raised to power n is equals to an bn, right? We have to prove this result. So firstly follow the same steps, prove for n is equals to 1. You will get ab raised to power 1 is equals to a raised to power 1 b raised to power 1. So what will it be? ab is equals to ab, correct? Which means the result is true for n is equals to 1. Assume for n is equals to k. You will get ab raised to power k is equals to a raised to power k b raised to power k. Okay, so this is what we have got. Mark it as a first equation. Now we have to prove it for n is equals to k plus 1. So just consider the left hand side of your equation. What we have? ab raised to power k plus 1, only left hand side. You can split the terms. You will get ab raised to power k multiply ab raised to power 1. Now from this equation you can fill in the value of ab raised to power k, right? What is it? A raised to power k multiply b raised to power k multiply ab raised to power 1. Now we will get a raised to power k multiply a raised to power 1 multiply b raised to power k multiply b raised to power 1. Now the bases are same though, so the powers can get added. A raised to power k plus 1 multiply b raised to power k plus 1. So what was on the left hand side? That was ab raised to power k plus 1. So this is the result that was required, because at the place of n we wanted to have k plus 1. This is how you can do these kind of examples. Only use the first equation and just follow these steps, follow the same basic steps, and you will get your desired result. All right, so with this we are done with our chapter mathematical induction. If you find any problem in attempting any sum or any of the example or any steps that I have explained in the video, you can contact me, you can DM me on my Instagram ID, which is given in the description, and also you can use the comment section. So before leaving my channel, please press the subscribe button and also the bell icon, so that I can make you these kind of videos on a regular basis to just increase your knowledge. Also share this channel with your classmates and other known ones as well, so just it will only assist them. All right, so see you in the next video. Nice to meet you all, and thanks for watching, guys. See you in the next video. Till then, keep practicing. Happy practicing. Bye bye.